Okay, so let's continue with different controllers from the family of PID. So we saw an example using a P controller. So the PID controller would be a controller that would have all these terms: a proportional term, an integral term, and a derivative term. Okay, so this is an integral term. You remember that the Laplace transform of an integral function is 1 over s of the Laplace transform of that function, and the derivative, it's s times the derivative of s times the Laplace transform of that function. For pi, it would be simply just only the proportional term and the integral term, and for PD would be just the proportional term and the derivative term. Okay. Now let's just look at the general term for the second order systems. So the general term for a second order system would be something like this: b divided by s2 plus as plus b us ys. Okay, and we can rewrite this transfer function into this format: omega n squared divided by s2 plus 2 zeta omega n s. This is not the right way to write this symbol, but it's close enough, plus omega n squared. Okay, so this is the general form of a second order transfer function. If you guys remember in ELEX 3130, you guys actually did this, but in the form of differential equation. So you had something like this: d squared, let's say vc dt squared plus 2 zeta omega n dvc dt plus omega n squared vc is equal to k omega n squared, something like that. Okay, so if you take this into the S domain or Laplace, if you take Laplace transform of this one, you end up with something like this. You might have constant k over here as well, but that's okay. We can just take this out and put it in a separate proportional transfer function. So this is basically what you've seen before. And there are, if you find the poles of this system, S, it's going to be equal to negative zeta omega n plus minus square root of zeta squared minus 1. Okay, so based on the value of zeta, you are going to end up with different frequency responses and time domain responses. So first of all, if you remember, this is called damping factor or damping ratio. Basically, it's an indication of how your oscillations, how the time domain oscillations are damped, and omega n is the natural frequency. So it's basically the point where the system starts to oscillate. So let me write this down, the point where the system tends to oscillate. make sure that you guys can see the whole thing. Yes. Okay. So let's just like see some of the different values that zeta can take and how this would affect our response. So there are zeta bigger than 1, zeta equal to 1, zeta between 0 and 1, and zeta equal to 0. Okay, so if zeta is equal to 0, it basically means that you have no damping. So you would have imaginary poles, right? So in this case, you would have imaginary poles. It's just like this term would be 0. So this is 0. So you just like have your poles. It's going to be plus minus j. You would have imaginary poles. So your poles are going to be here. And this system, if you remember the imaginary axis, basically each point here is correspondent to a frequency, and it means that your time domain response, it's gonna look like something like this. See, the oscillations are not damped. You have AC, a steady state. You have like oscillation all the time. So this is like the time domain. Okay, so that's basically called no damping, or undamped system. Okay, if zeta is between 0 and 1, again, this you're gonna have a complex term. You have a real part, you also have imaginary part, so you end up with something like this. Okay, and if that's the case, the system is underdamped. Means you have some damping, but it's not enough. You're still gonna have some oscillations, and those oscillations would eventually die, and then you would just like in the limit, you would reach your final value, the target value. If zeta is equal to 1, then you would have absolutely no imaginary part. This would become 0, right? And your pole, it's just gonna basically, you have two poles on top of each other, right here. And this system, it's called critically damped. Right? Many times we want our system to be like this. If the system is critically damped, if you're trying to reach this target value, you would reach that target value very fast. That's why, like, many times you would have, you would want your system to be critically damped.